Yes, very good. I am Dr. Kelly Cline. It is my great honor to teach here at Carroll College. I get to teach all the most fun classes here, stuff in math and physics and astronomy. And it is my great pleasure to give this, which is part of an ongoing series of public presentations and fun, cool, exciting topics in current scientific research. And so tonight we're talking about NASA's Dawn mission. Just an absolutely wonderful, wonderful mission using some new technology to make some amazing discoveries about our asteroid belts to orbit around a couple of these objects. And so I just have to tell you all about it. So that's what we're talking about tonight. There we go. So there's one of the images that's been brought back by Dawn, plus a little image of the spacecraft itself. Excellent. So we're going to talk about, first we'll talk about what is the asteroid belt itself. Where does the asteroid belt come from? What's that all about? And the Dawn mission is powered by an entirely new sort of propulsion system. Not ordinary traditional rockets. It's powered by this ion drive propulsion system. And that has allowed it to orbit around Vesta for a year, one asteroid, and then it broke orbit, left and went and orbited around another asteroid. It's still in orbit around Ceres. It's been there for more than a year now. It's done a lot of really interesting and wonderful things. So here it is. It was launched in 2007, and this engine design is just amazing. It gives about 10 times as much propulsion per pound as a normal chemical rocket, and so it could orbit one for a while, break orbit, and then go explore something else, which is just amazing. Dawn has found Vesta to be a dense, rocky world, all sorts of craters there, and it explains a certain category of meteorites we've seen fall into the Earth. On the other hand, Ceres is a very different sort of world. Lower density, maybe it has some ice in its mantles. A lot of people speculate about that. And it's found these interesting bright spots on its surface. And it's absolutely revolutionized our understanding of these objects. Up until the Dawn mission, these were kind of, the best images we had from the mighty Hubble Space Telescope were still kind of blurry sort of things. I mean, when you're 100 million and more miles away from an asteroid, it's really hard to see any detail at all. And now we've got very detailed, high-resolution photos. We have all sorts of wonderful images of all the craters and mountains and grooves and cracks and all the features on the surface. They've gone from a little blurry sort of blob in the telescope to suddenly worlds with details and amazing discoveries. So Dawn has been a fantastic mission. So here it is. Let's talk the history of the asteroids and the asteroid belt. On January 1st, 1801, astronomers, an Italian astronomer, announced the discovery of a new planet, a planet that had not been found before. The planet Uranus had been discovered about 20 years before this, and then in 1801, astronomers discovered an entirely new planet. The planet was named Ceres, found to be about 600 miles in diameter, orbiting the sun between Mars and Jupiter. The next year, another planet was discovered. The planet Pallas was discovered, about 350 miles in diameter. In 1804, the planet Juno was discovered, 175 miles in diameter. In 1807, Vesta, there's the other one that's been visited by Dawn. Vesta was discovered. All of these orbited between Mars and Jupiter. A few years later, the planet Neptune was discovered, way out beyond Uranus. And by 1851, there were 23 planets in our solar system. And then, in the late 1800s, astronomers started building bigger and more powerful telescopes, and they discovered that there were lots of planets in our solar systems. And lots of really small ones in particular. Tons of these tiny little planets orbiting between Mars and Jupiter. And so then, rather than, adding thousands of planets to our solar system, they created this new category, this idea of asteroids. There's this asteroid belt in our solar system. And so that kind of reorganized our understanding of the solar system. And said, no, planets are big things. Asteroids are these little things that orbit around there. And there are two major types of relatively small objects that orbit our sun. We have the comets. They spend most of their time in the far outer solar system. They have lots and lots of ices, water ice, dry ice, carbon dioxide ice, methane ice, ammonia ice. They spend a lot of time in the outer solar system, and then they fall into the inner solar system, are around the sun for a brief period of time where they melt and vaporize, and they put out great tails and all these sorts of things that are wonderful to see. Asteroids tend to have more circular orbits. They tend to be made of more rock and metal, although they can have a substantial amount of ice in them too. They tend to orbit closer to the sun in the neighborhood of Jupiter or Jupiter to Mars. And so we want to ask, well, why is that? Where did all these asteroids come from? But that's really not the right question, because when we look at our theories, our understanding of where did our solar system come from, Well, originally, we went back 4.5 billion years ago so we could see the formation of our sun and the planets. Originally, there were lots and lots more of these small objects. When our solar system started 4.5 billion years ago, it's this spinning cloud of gas and dust. And most of the stuff falls into the center to make the sun, and then gravity pulls clumps and blobs and chunks of it together to form other objects. So initially, there's lots and lots of small objects everywhere. If you went 4.5 billion years ago, our solar system is crammed with comets and asteroids and all sorts of small things. And then gradually gravity pulls them together and forms the Earth and Venus and Jupiter and all the other planets. So the real question is, well, where did the planets come from? Those are the new things. These comets and asteroids are older. So here's another interesting discovery. In the 1860s, this is Daniel Kirkwood, and he was mapping the position of all these asteroids, and he found that they're not just smoothly scattered through space. I guess the first thing you need to know about the asteroid belt is, if you've ever seen the movie like The Empire Strikes Back, where you got the Millennium Falcon dodging through all these asteroids, smashing into each other, that's not like our asteroid belt at all. Not even close, not even in the ballpark. Our asteroid belt's more like, here's a rock, and then, 20 million miles. Oh, there's another one, and then another 30 million miles. Oh, there's another one too. I mean, we have space probes that fly right through the asteroid belt all the time, and we never worry about them hitting stuff because space is really, really big. Space is vastly big. And so Kirkwood here is studying the distribution of these objects in the asteroid belt, and he found that asteroids are not smoothly distributed. There are places where you don't have asteroids. So on this axis, we have distance from the sun. So 1 AU is the Earth's distance from the sun. So here's 2 AU. That's twice as far away from the sun as we are. And then, a whole bunch of asteroids. And then right around 2.5 AU, there are no asteroids there. No asteroids orbit at that particular distance from the sun. And you go a little bit farther, and plenty more asteroids, and then, at this point, there aren't any here, and there aren't any here. And so there are these odd gaps in the asteroid belt. And when people studied that further, they found that there's something seemed to be going on with the orbit of Jupiter there. There's something going on with Jupiter to cause this. So here's the math. Here's how it works. Jupiter is about 5 AU from the sun, 5.25 AU. Jupiter takes 12 years to orbit the sun. So let's look at one of these gaps, that one at about 2.5 AU from the sun. If there was an asteroid there, it would orbit the sun in exactly 4 years. Now that's kind of cool because 4 is exactly 1/3 of 12. Jupiter orbits the sun once every 12 years, and an asteroid in that place would orbit the sun every 4 years, and so so this would do exactly 3 orbits for every 1 Jupiter orbit. So this would go around 3 times, and Jupiter would go around once. And so there would be what we call an orbital resonance there. They would kind of do this little dance. They'd all line up exactly at the same place again and again, and there aren't any asteroids there. And all these gaps correspond to these simple whole number resonances. Oh, it's this times this, it's some whole number fraction. Why should that be? For 100 years, this was a great mystery. Why would the gravity of Jupiter do that? Why would that happen? It has to have something to do with the gravity of Jupiter. I mean, Jupiter's a big object. Jupiter's 2.5 times more massive than all the rest of the planets in our solar system combined. So, it's a really big object. It has strong gravity, but why there? You would think if Jupiter has some kind of evil vendetta against asteroids, what's it going to do? Well, it's going to get rid of the asteroids that are nearby. But it doesn't do that. It's for some reason, go back here. I'll flip back to here. Yeah, it goes back. Jupiter gets rid of the asteroids here. These guys over here are way closer to Jupiter. So are these guys. But those guys go away. So that's the question. Why does that happen? Why do these exist at these resonance points? And that was a great mystery until the computer era. Until we had big, powerful, amazing supercomputers that could figure out what would happen. Because it turns out if I want to solve Newton's gravity equations to figure out how asteroids orbit the sun, well, if I'm just paying attention to the sun, that's easy. We can do that. But then you throw Jupiter into the mix, and then it's getting pulls from Jupiter, and we can't solve that on pencil and paper. We need computers. We need to be able to run experiments and see what happens. And what the computers showed us, the first major experiments were run in the early 1980s. This is Jack Wisdom at MIT. And he ran these big, amazing simulations. And what he showed was that when you put an asteroid in these orbits that resonate with Jupiter's orbit, they get tweaked, they get stretched, they get distorted. These lining up again and again and again in the same place causes the orbits of the asteroids to, I think the technical term is they go all wonky. It messes them up. It makes them very elliptical. Here's one of the simulations. So he ran this thing for 20,000 Jupiter orbits. So that's, you know, that's a long time, hundreds of thousands of years. And he found that it makes these orbits do all these weird things, go up and down, and get very strange and stretch out and do strange things over time. And so what happens is, if you put an asteroid in that place where it resonates with Jupiter's orbit, the orbit's going to get stretched and squashed, and it's going all these different ways. And what will happen is it will get to the point where it will cross the orbit of Mars. And then, of course, if it crosses the orbit of Mars, then sooner or later, it will either smash into Mars, or it will get close enough to Mars that Mars's gravity will tweak it and fling it off out of the solar system. And some of these things could get tweaked even so much that they would even cross the Earth's orbit. And so that's what happened to them. What happens is that all the asteroids, there used to be a lot more stuff in that area. If you add up all the stuff in the asteroid belt, it doesn't amount to it. It's a tiny percentage of the Earth's moon. There used to be a lot more stuff in the asteroid belt, but Jupiter's gravity messed with it. Jupiter, all these resonances with Jupiter's orbits, flung all this other stuff out of there. They crashed into this, they crashed into that. And so what you have left in the asteroid belt is a small population of objects, just a few things left over when Jupiter's meddling, nasty, mean gravity got done with tweaking and stretching and squashing and messed with these orbits. So, I mean, that helps us answer the question of why there are any asteroids at all. I mean, there are very few asteroids here near the Earth's orbit. There used to be a lot more stuff here, but this stuff all kind of gathered together to form the Earth. There are very few asteroids out in, say, Saturn's orbit. There used to be a lot of asteroids and things out there, but then gravity gathered that together to make Saturn. So what happens is, the reason why we have these asteroids is because Jupiter prevented this stuff in this area from ever forming a planet. If Jupiter hadn't been there, if there was no Jupiter, if you go back 4.5 billion years and you erase Jupiter out of the history of the solar system, then probably there would have been another planet that formed there a little bit farther away from the sun than Mars. But Jupiter's, all these resonances and all this chaos and all these tweaking of the orbits stirred the stuff up, destroyed most of it, flung most of it away. And what you have left are a few stragglers, a few survivors of this, about meddling from Jupiter. And that's what it's all about. So, there's the asteroid belt. That's why it is there. Yeah, there it is. If you put all the asteroids together, you know, some people wonder, well, was there a planet in the asteroid belt? Well, no, there isn't enough stuff there. You put all that together, you only get about 4% of the mass of our moon. It's a tiny, tiny fraction of stuff. You only get about 20% of the mass of Pluto. A teeny fraction of the mass of Mercury. Forget about it. So the asteroid belt doesn't really have a lot of stuff in it. And right here, you're looking at a third of the asteroid belt. That's it. Ceres has about 1/3 of the mass of the asteroid belt. All the asteroids except for Ceres contain about 2/3 of the mass, and Ceres is 1/3 of the mass of the asteroid belt. And it's something else. Remember, you know, back in the 10 years ago when they're all trying to figure out what to do with Pluto, they said, okay, Pluto hasn't cleared out its orbit, so it's not a major planet, but we'll call Pluto a dwarf planet because Pluto had enough gravity to shape it into a ball. Ceres is the one asteroid that can do that too. Its gravity is strong enough that Ceres forms a ball. It's a sphere. It looks like a world sort of thing. So Ceres is a dwarf planet. It's the only asteroid in the asteroid belt that is a dwarf planet. All the other asteroids are kind of potato-shaped and oblong and all that because they're not big enough. They don't have enough gravity to squish them down into a nice, pretty ball shape. But Ceres is a dwarf planet as well. And when we study Ceres, we find that it has an intriguingly low density. You know, rocks and metals and things like that. We think most asteroids are being mostly made out of rocks and things. Those tend to have densities like 3 or 4 times the density of water. Ceres is only double the density of water. So this causes some people to speculate that maybe there's some lighter material. Ceres must be made of lighter materials. Are there gaps in it? Are there holes in it? Are there cracks and fissures in it? Or is there lighter material? Some people speculate that there could be ice inside of Ceres, that maybe Ceres has a big mantle of ice underneath its rocky crust. Here's the other asteroid that Dawn has visited. This is Vesta. We're going to talk about a potato shape there. But this is the second largest asteroid. Vesta has about 10% of the mass of the asteroid belt. So we can say that the Dawn mission has now visited 40% of the asteroid belt, because it's meant to these two. One has 1/3 of it, the other has 10% of it. There is another asteroid that it's almost exactly the same diameter as Vesta, asteroid Pallas, but Vesta is significantly more massive. Vesta is a very dense asteroid. There it is, 3.5 times the density of water. That tells me that this is a rock. This is a hunk of metal. This is there are no big gaps and fissures or ices in there, not much anyway. So astronomers figure that Vesta's got to be some dense, thick chunk of rock, ice, and metal, where Ceres maybe has a lot more lighter things in it. So that was the idea. That was the idea. Let's send this Dawn mission out there. We can send it to a couple asteroids. Let's send it to 2 big ones, and let's send it to 2 totally different ones. And these asteroids are as different as night and day. They're different chemical compositions, different densities, different structures. And so by orbiting these, well, then we can do all sorts of interesting things there. We can learn about these 2 extremes of the asteroid belt. So here's the other thing I got to tell you about. See, Dawn has these amazing engines. I mean, up until this point, all of our space probes have been powered by traditional rockets, but this is powered by ion drive, which promises to give us an absolute revolution in the exploration of our solar system, because they are way, way, way more efficient than traditional chemical rockets. So, what's a rocket? How does rockets work? So we got to talk about this. I love this little diagram there. We got this guy. He's on a cart and he's firing cannonballs out of a cannon. I think I should have one of these for my physics class. Wouldn't that be awesome? Okay, now students, we all need to go outside now. I'm going to fire my cannon now. That would be so cool. So anyway, what happens? The guy's on this. He fires the cannonball goes forward. And according to Newton's 3rd law of motion, for every force forward, there's a force backward, so that pushes the cart backward. So if the guy on the cart shoots the cannonballs a bunch forward, then that sends his cart backwards. That's how rockets work. They shoot their fuel out, and they push against their exhaust, and that pushes them forward. And so that's how they work. So a traditional rocket uses chemistry. So we got some sort of fuel here, and rockets want to go in space, so you got to carry your oxygen along. And so you shoot your fuel in here, your oxygen in here, and then you got something that ignites it, and then blam, you get some great big exciting chemical fiery reaction going on in the chamber, and then you only allow the stuff out in one side through the nozzle, and that shoots the gases out on one side, and so then the rocket goes the other way. That's how it works. Different rockets use different chemical reactions. When the space shuttle was going up, its favorite chemical reaction was just hydrogen for one tank and oxygen in the other. Hydrogen and oxygen react together to make a wonderful, glorious substance I like to call water. So that's the exhaust coming out of the space shuttle. When they used to launch that, those big clouds behind it were just ordinary steam. Turns out hydrogen and oxygen reacting to make water gives off a vast amount of energy. Other different uses solid fuel or liquid fuel, all these sorts of things. But again, chemistry happens. It's hot, it's exciting, it's energetic, and then it shoots the exhaust out the backside. And the efficiency of a chemical rocket is dependent on how fast the exhaust goes out. And so its exhaust velocity tends to be somewhere in the neighborhood of 2, 3, 4, 5 kilometers per second, 2 to 3 miles per second, something like that. So here's the so chemical rockets have their advantages and their disadvantages. For one thing, they're heavy. They got a lot of stuff, because you got to carry these big, heavy chemicals around there. And then what chemical rockets do is they give you a huge, vast, enormous amount of force for a very short time. So if you want to launch something into space, you got to use a chemical rocket. We're going to be using chemical rockets to put things into orbit from here on out for as long as we can see. Because in order to get into space, you got to push really hard to escape the Earth's gravity, super, super hard for, a couple of 20 minutes that it takes to get up into orbit. And then you've used up all your fuel, but that's fine. Okay, so that's how it works. But as you're doing that, I mean, whenever we launch a rocket, a shuttle, or anything like that, what you got to know is that the vast majority of that big thing standing on the launch pad there is the fuel, is the chemicals. That you actually measure, okay, the space probe with the instruments and the computers and all that, that's like 0.1% of the mass of the thing on there. It's just dominated by the mass of the fuel, and then, the fuel tanks, because you got to have a huge fuel tank to hold it, all that sort of thing. And then by the time you've burned away all that fuel, you've lost more than 90% of the mass of your thing. That's what a rocket is. It's mostly fuel, and then you got your tiny little space probe at the end, and we hope that it survives and all that sort of stuff. And so they're limited by this. They give a huge amount of force, but for a short time. And once you're up in orbit, all our other space probes have been powered by that. Whether you're talking about the New Horizons mission to Pluto, or our Juno mission out to Jupiter, which is going to arrive this summer, you turn on your chemical rocket, it fires, it shoots, and it burns for, 5 minutes, and then it coasts, for 10 years to get out to Pluto or something like that. That's how it works. A huge reaction for a very short period of time, burning away a vast quantity of fuel. This is what an ion propulsion is so much amazingly better than that once you're into space. So first you got to have your chemical rocket to get into space, but once you're there, ion propulsion is way, way, way more efficient. So we've got to talk about that. What is an ion? I'll tell you what an ion is. That's what happens to an atom. Let's see, what are atoms made of? They got their neutrons and protons in the nucleus. Protons are positively charged, neutrons are neutrally charged, and then you got your negatively charged electrons hooked around there. And normally, an atom has the same number of negatively charged electrons, it has positively charged protons, so most atoms are neutral. So they've got as much plus as minus, so they don't care if you put any charge or voltage around them, they just sit there. But if I take that atom and I steal one of its electrons, or two of its electrons, or three of its electrons, well, I take them away, and so what does it do now? Well, it has more of the protons, more of the positive charge, than it does the negatively charged electrons. So now, it's an ion. Once an atom becomes charged by either gaining or losing electrons, it becomes an ion. And now we can push it around. So once I've given an electric charge, what I can do is now I can put a grid over here where I can give it a whole big strong amount of charge. So if I take these negatively and positively charged grids and I put 50,000 volts between them, well, now that's going to pull this thing around. So now my ion's going to go shooting over in one direction or another, depending on which charge it has. And that's the idea of an ion engine. The point is, I just need to get my fuel up to high speed. So if I can take my atom and strip away some electrons and yank it over here, push it over here really fast with this high voltage sort of thing, I can speed it up to enormous speeds. Far, far higher speeds than anything you can get from any chemical, ordinary rocket. And so that's how it does it. That's how Dawn works. Dawn has this xenon gas. Now, xenon gas is completely and totally inert. It's one of these gases like helium that doesn't do any chemistry with anything ever. But it happens to be the sort of thing that we can make beautiful ion engines out of. That's a plus. That's a feature, not a bug in an ion engine. So you got a bunch of xenon on board. It started out with almost 1,000 pounds of xenon. And then you bring it in here, you strip off some electrons, you zoom it up to enormous speed, and then you shoot it out the back, and then you got to get rid of those electrons too so that your spacecraft doesn't build up a negative charge. And that's how it works. And the energy from it, rather than coming from chemical reactions, the energy is electrical. So Dawn has these huge, giant solar panels, and that's what drive the engines. It has these whole solar panels. Those solar panels are not just there for turning on the cameras and the computer and all that. No, those solar panels are there to create the voltage which drives that amazing, powerful ion engine. And so, for the exhaust velocity for an ion engine is about 20 to 50 kilometers per second. That's 10 times faster than a chemical rocket. So as a result, that means, everything, the limitation of getting things to space is that it's heavy. That's the problem. It's so expensive. It costs thousands of dollars per pound for everything you send to space. So if I can take the same amount of rocket fuel and get 10 times more thrust out of it, I can do amazing things. That's what Dawn does. That's it exactly. Its ion engines can get approximately 10 times more propulsion per pound of fuel. And that allowed it to do its amazing stuff. We have never, in the entire history of NASA and space exploration, nobody has ever sent a space probe to go orbit around some planet or anything like that, and then leave, and then break orbit and go somewhere else. By the time you get there and enter into orbit, they've used up their fuel, that's it. The only time we've ever broken orbit around anything was the old Apollo moon mission, because we had to get Neil Armstrong home, because his wife was worried about it. So, but with our little computerized robot space probes, whatever, you put them in orbit around Saturn, and you use them until you're done with them, and you just leave it there. You turn it off and call it good. But this is amazing. This is wonderful. So for the very first time, it entered orbit around Vesta, studied Vesta for a year, took all sorts of pictures, great readings, wonderful stuff, and then it still had enough fuel that it could blast off again, break orbit, fly away over here. Hey, let's explore Ceres now. Go into orbit around Ceres, and now it's been there for a while. That's never happened before. We've never had any of our unmanned probes have enough fuel left to do anything of this general nature. That's wonderful. On the other hand, another big interesting thing about these ion engines is that they operate for long periods of time slowly. Chemical rockets are fast, so NASA engineers are used to working their orbits and, we're going to do a burn here. So you fire up the engines of the Cassini space probe, they burn for 5 minutes, and then it spends 10 years going to Saturn. With this sort of thing, no, you turn it on, and it's not a lot of force, it's just a force over a very long period of time. So then you turn it on for weeks or months. And you accelerate faster and faster and faster as you're getting closer. And then about halfway there, then you turn the ion engines around, and then you decelerate, getting slower and slower and slower going in. It's the sort of thing you turn on for a very long period of time, accelerating more and more and more. This is a revolutionary technology. And this is the sort of thing we're going to be seeing in a lot more space probes. There's even potential that, in the distant future, this may be how we get people back and forth from here to Mars. You'll never orbit on an ion engine. You need a lot of force. You need a chemical rocket for that. But once you're there, this is an amazingly efficient way to get around. So you can do some really fun things with this. All right. So there's the ion engines. There's the space probe. Let's talk about the science. And when we talk about Vesta, one of the big, giant, wonderful mysteries which has been solved by the Dawn space probe has to do with a really fascinating category of meteorites. These are rocks from space that we found here on Earth. So, now, meteorites, there's an example here. There's a very typical one that, you find it down here. Most of them are made of nickel and iron. They fall, well, most of them burn up in the Earth's atmosphere, but you got rocks in space. So, we see them streaking across the sky as shooting stars, but every now and then something big enough falls into the atmosphere, falls down to the ground, and we find it. And they've been found all over the world, and particularly in Antarctica, because they've got these big ice sheets there that are very thick. And so if you find a rock on top of the ice sheet, well, you didn't come from under the ice sheet, so it must have fallen from space. Great place to find things. And when we study these things, we can learn amazing things about the universe. Because first of all, they have totally different mixtures of chemicals and minerals and atoms and things than what we find here on Earth. All the rocks from all over Earth has many, many very different, very interesting kinds of rocks. But they all have some simple things in common. And when we study these rocks that fell to the Earth from space, they look very, very different. By studying the chemical composition of all these different meteorites, we can put them into these different categories and begin to figure out where a bunch of them came from. So, let me tell you about a certain category of meteorites. Actually, 3 categories of meteorites. We call them howardite, eucrite, diogenite meteorites. Because, geologists make up cool names for all these awesome minerals that they can find. Here's an example of a howardite meteorite. So these things are not these typical iron, nickel sort of meteorites. These are kind of unusual sorts of things. Only 5% of all meteorites fit into this category. This is one that's been sliced across, and it's very rock-like on the inside. Not a typical meteorite at all. And they have these different mixtures of these minerals, these different chemical compositions in there. And the question is, well, why? Most meteorites are just nickel and iron, so if you bring your magnet next to them, they'll stick to them. A lot of them are magnetized. These are not like that. These are more stony meteorites. So what are they? Where do they come from? Well, what we do is you drill a sample of them, and then you say, well, how much of these different elements do you have? And one thing we like to do is study, well, what percentage of this is iron, and what percentage of this is manganese? And we find that these are really different than what we find here on Earth. This is a plot. Okay, so on this axis, we've got the amount of iron in the meteorite. And on this axis, we've got the amount of manganese, which is a metal in the meteorite. And so what we find is if we study Earth rocks, they all lie along this line. I mean, some of them have small amounts of iron and manganese, and some of them have more amounts of iron and manganese, but they're pretty much in proportion. Among Earth rocks, if you've got twice as much iron, you've got twice as much manganese. If you've got 3 times as much iron, you've got 3 times as much manganese. And so they all lie along this line. On the other hand, there are other groups of meteorites where we can find they have totally different things. For instance, these red ones up here, notice that they've got a lot more manganese for the same amount of iron. And so there's this whole population of them that we've identified, those are from Mars. So these are meteorites where, I don't know, somehow some volcano on Mars belched up some big rocks, they floated through space, fell down to Earth, and we found them. And we've even found a bunch of meteorites from our own moon that we can find. And so you can see, oh, those have not nearly as much manganese for a certain amount of iron. They exist in proportion down here. And then these ones, these HED meteorites, are way up here. They have enormous amounts of manganese. Way, way, way more manganese per iron than you would find in any rocks here on Earth. So, back in the 1960s and 70s, people are, squinting at Vesta through their telescopes, and they can do very basic spectroscopy, taking the light from Vesta, taking that light, breaking it up into a spectrum of colors, and all the different types of atoms interact with light differently. And so they began, and they said, ooh, there's all this stuff on Vesta, there's a lot of manganese on Vesta. There's more than you would expect. And then take the ratio of manganese to iron on Vesta. And they could make some rough estimates with telescopes throughout the 70s and 80s. And so the hypotheses were proposed. are these guys, these howardite, eukarite, diogenite meteorites. All three of them are different minerals, but they all have this kind of same relationship between their manganese and their iron, and so the hypothesis was proposed. Are these guys from Vesta? Is that where these rocks came from? And this is why they all have something in common. And so then people began to speculate, well, if this is true, if these are from Vesta, then well, Vesta must be an interesting place because it has three very different categories of rocks in it. So maybe, oh, that told me, maybe Vesta, so this is the hypothesis, this was the dream, this is the speculation. Back before the Dawn mission, you know, very primitive telescope sort of measurements tell us, Vesta's got a lot of manganese. And then, well, maybe these meteorites came from Vesta, and there's three different types of them, so maybe Vesta is something which has kind of settled out. Maybe it has like a mantle and a crust, you know, where the dense stuff sunk to the core, and then the lighter stuff, you know, rose to the surface. So that would explain why you would get different minerals there if you got different things and different densities. Maybe Vesta at least is a heavy differentiated object to produce those sorts of things. And so people wrote papers and they speculated and they did lots of math, and for decades, that was all we had. Some speculation, some meteorites, some cautious telescope observations, and a lot of speculation. So that was one of the key points of the Dawn mission. Let's go there. We got all these people speculating that these meteorites all came from there. Let's see if that's right. So that was one of the reasons why Dawn was chosen to go to Vesta. So it orbited around Vesta between July of 2011 and September 2012. And one thing it did was it performed very detailed studies of Vesta's chemical composition. And you know what it found? Tons of manganese. The ratio of manganese to iron is exactly what we find in these meteorites. The relationship there is exactly what we see here. And further, by orbiting around it, you can figure out the gravitational field of Vesta. Where's the dense stuff? Where's the lighter stuff? And it finds, oh, beautiful, look at this. Vesta has a more dense core. It has a lighter crust. It is what we call a differentiated object, like the Earth. The Earth, our densest stuff, most of it sunk to the core. The crust is actually made up of the lighter rocks and metals and things. Vesta is similar from that. And the eukaryotes came from Vesta's crust. Diogenites came from, well, we're going to call it Vesta's mantle. And then howardites are kind of a mixture of the two. I don't know if we quite really have a core the way the Earth does, but certainly a crust and a mantle. And so that, and plus, these pictures are just wonderful. You can see, you know, we've got all these craters covering Vesta all over there. Before Dawn got there, we had these blobby, blurry, smeary pictures, which were heroic things out of the Hubble Space Telescope. And now we've got thousands and thousands and thousands of detailed pictures all over the surface. Wonderful, wonderful stuff. Check this out. This is a picture of Vesta's south pole. And look at this shape here. We got this shape here, and then you got all these round things around it. You know what this is? This is a crater. This is an impact crater. When we look at Vesta, we see that, you notice how it wasn't round shaped? It's got kind of chunks taken out of it. There were two enormous chunks taken out of Vesta near its south pole. The team is named Rhea Silvia and Venenia. There we go. Huge craters, enormous craters. If these impacts had been any bigger, they would have destroyed and obliterated Vesta completely. Two craters, they've been estimated to be 250 and 310 miles wide, which is pretty good considering Vesta's total diameter is only 325 miles. When you got a crater that occupies about 90% of your total diameter, that's fantastic. We can also see that because these craters, these big things are pretty ancient because, you got all these other little craters on top of them. Craters are what happen to a planet or an asteroid when nothing happens to a planet or an asteroid. Because there's junk in space. There's always junk in space. Any object floating through space is going to have things hit it. Now the Earth has very few impact craters on it because we have erosion and wind and water and we have volcanoes and we have plate tectonics and all these things are constantly erasing craters. But when I see an object which has just tons of craters on it, that means, well, it doesn't have erosion and it doesn't have volcanoes and it doesn't have plate tectonics. And so when I look at a region on the surface, I find that, look at all these craters, this must be an old region. And so you got this big, huge impact, all these fractures going out there, and then lots of craters on top of it. That tells me that these are very, very ancient. So probably these impacts happened long ago. And here's the big idea. These big, giant impacts, these huge craters which almost destroyed Vesta completely, would have knocked huge amounts of debris into space, thrown all sorts of junk, all sorts of rocks into space in every direction. And some of them would have fallen to Earth. And so those two impact craters, the ones we're seeing, this big fractured out region there on its south pole, probably exactly where all those meteorites come from. Those ones that are still following to Earth every now and then, that's debris, leftover junk from those impacts which almost destroyed Vesta completely. That's where the HED meteorites come from. Probably. Cool. Here's another wonderful thing, another awesome. So okay, so our story of, based on this, our story of Vesta is Vesta has a violent past. Lots of exciting things happen here. Two enormous smash giant impacts. That's why Vesta is a heavy, dense sort of object. It was a place where there was a lot of violence, a lot of heat. This would have kind of melted Vesta, which caused the dense stuff to sink to the center and let the lighter stuff float to there. That's why it's such a very dense object. Would have eliminated any bubbles or anything like this. Anything like a water or any of these lighter icy materials would have been driven away by such a violent event. But probably the strangest thing that came out of Don's discovery is that there's all this dark material, this dark, dusty sort of material, all covering the surface of Vesta. And when it does the chemical analysis on this, you know what it finds? Water. Hydrated minerals, different minerals that have water locked up in different places. And so that's exactly the opposite of what we would expect. Wait a minute, we've told the story that no, the Vesta is this place where there were these impacts with melting and lava and exciting infernos, and then, but where does the water come from? Because, you know, volcanoes get rid of their water really fast. So here's the speculation. Here's the hypothesis. Here's the guess. Maybe these are, and we find these on the surface, where we're studying the surface. Maybe this is just kind of a light dusting material on the surface. Maybe these impacts brought in, maybe they had the watery sort of material that smashes into Vesta and then contaminates, covers the surface of Vesta with all this dusty material, this hydrated stuff. And then once you dig down into Vesta, then you're not going to see much stuff in there. That's an idea. And nobody knows. And this is fun. I mean, there's so much data that's been poured in. You know, tons and tons of pictures, lots of chemical analyses, all these different forms, and now people are going to spend the next 10 years pouring through this data, trying to make sense of it, trying to assemble some crazy jigsaw puzzle to tell us about the history of this strange object Vesta. Where did it come from? Why is it there? How did all this happen? How did all these pieces come together to create this wondrous, strange, amazing world we call Vesta? We're just beginning, just beginning. All right, let's talk about Ceres. All right, so Dawn entered orbit around Ceres in March, a year ago. So it's been there, March 6, 2015. It's been there for more than a year. So what it's been doing is during that time, first it started a very wide orbit, taking some big overall pictures. And then over time, you know, the astronomers are like, okay, coming closer, so we're coming a little bit closer. Orbit here for a couple of months, taking pictures, great. We want more close-ups, so I'm coming closer. It's now down at really low altitude. It's down at an altitude 130 miles above the surface. So it is closer to the surface of Ceres than the space station orbits around the Earth. So really, really close, because the closer you are, the better, the more high-resolution pictures you can take. We see impacts, we see craters and asteroids, you know, all over the surface. Remember, Ceres is the one that's round, and Ceres is the one that's low density, so everybody wonders, well, does that mean there's ices down there? Is there water? Is there methane? Is there ammonia frozen under that surface? We do not see the ices on the surface, but we would not expect to see ices on the surface because it's relatively close to the sun. The sun would bake those away. Any ices on the surface would be baked away. Check this out. This is really cool. This is a mountain on the surface of Ceres. It's called Helena Mons. And it's 3 miles tall. It's the largest mountain on the surface of that. That's interesting. We know where craters come from. Craters are easy. Junk in space hits Ceres, makes a hole, and that's a crater. But mountains. Now look at this. Look, it's got this kind of domey, pyramid-y sort of shape around here, and then it kind of goes into this little plateau over this direction. How did that happen? Why? Well, we know how mountains are created here on Earth. You got, you know, the Earth's mantle is liquid and churning, and so this pushes the plates together, and where the plates smash together, you get the Rocky Mountains. That's not what's going on here. We have volcanoes. Volcanoes, you know, erupt out, and you build a great big Mount St. Helens or stuff like that. That's not what's going on here either. What is it? All sort of mountains on the Earth are caused by, you know, this churning heat mantle inside the Earth, pushing up on the crust, stretching the crust. Is that what's going on here? Does Ceres have a liquid mantle? Is this a place where there was an upwelling of liquid that then pushed out in the crust and pushed the mountain up or something like that? We don't know. If it was liquid, with its low density, I would expect this to be, some people have wondered, is there liquid water inside of Ceres? If we were to drill down a couple miles in, would we find warm water churning up down there? I have no idea how it would still be liquid. Usually asteroids cool off pretty good, but this is a fascinating feature. How do you create a mountain there? Nobody knows. Nobody knows where this comes from or how. Wonderful stuff. Check this out. Here's a crater. This is called Oho crater. So a big crater there. It's got all this light kind of material around the edge. We'll talk more about this. But this is interesting. Look at this. Look at this. It's a crater with a thingy off the side. You know, nice big round. When rock hits planet, rock hits asteroid, rock makes round hole. That's how it works. But look at this. It's got this. I think geologists have a term for this. They call this a slump. Okay, good. It's a big hole where you got this kind of linear, straight feature there. This happens. We see this in places here on Earth where, shoot, this happens sometimes in Florida where they pump all the water out and then the land goes slump. You know, where you've got material underneath and then the crustal material falls down. This is exactly like that sort of stuff here. We see this sometimes in the Arctic where you've got, permafrost that then melts, flows away, and then the land goes ka-chunk. Because all the stuff below it went away. Look at that. This is one of the most interesting things. People are like, what happened here? Is this connected to the impact? Did the impact smash in there, and then what? Did it melt away some water, the water left, and then the land collapsed above it? Was there a hole in there somehow? Is there some sort of geologic activity? Nobody knows. Nobody knows what this is all about. Look at this. Look at this. This is beautiful. You got this big old crater there, nice, cool crater, fun stuff. And then you got these grooves, these big wrinkles across the surface. What is that from? Why did that happen? One idea is, okay, let's stick with nice, boring impact craters. Maybe something happened, and these are kind of rippledy, earthquakey shock waves that like stretched and squashed across the surface of Ceres. Maybe. Interesting shapes, though. Kind of valleys and things. I mean, there's no atmosphere on crater. There's no erosion. Again, could this be stretching and squashing? Is this some kind of tectonic activity here, wrinkling the crust? This is fascinating. This is the last thing. If you expected Ceres to be just some dead, rock in space, you just expect it to be covered with craters all over and nothing else. But this is interesting. Nobody knows what that is. And then here was the most fun thing. This is what I was watching. Last fall through the spring, as dawn was getting closer and closer, leaving Vesta going towards Ceres, the news came up from NASA. There are these bright spots on Ceres. There are these things on Ceres that are bright and shiny. And so we took better and better pictures of what are they, and they found this whole series of these bright spots on Ceres. They tend to be found in younger regions where you have like a fresh crater. Like here's a new crater that's, very young, only 10 million years old. Something like that, a new crater, and it has these bright spots and these bright regions. And at first, everybody was thinking, could this be water? Again, low density Ceres, maybe it's got ice under its rocky crust. Is this a place where, something comes in, smashes into things, makes a crater, and then you get an eruption of steam or ice or volcano of water or something like that coming through to the surface? That's what everybody's looking at. This is the very brightest spot on Ceres, right in the middle of this relatively young crater here. But when they measured that, they found that that's not ice. That is not frozen ice right there. When they did the chemical analysis, they found it's a type of salt. But not ordinary salt. This isn't sodium chloride, the sort of thing you put on your eggs. No, this is, don't put this on your eggs. This is magnesium sulfate hexahydrate. So it's a messy salt, okay. But the point is, salts dissolve. So why would we see that in places where you've got where you've got a young crater? Now one idea would be, the thing that smashed into Ceres brought the salts with it. But then you wouldn't see that in several different craters in different places on the surface. So no, this is native salt. This salt was born and bred here on Ceres. So why would you see this in young regions? Well, okay, we've got a young region, something smashes in there, it's going to dig things up, it's going to break through this rocky crust. So material from below, why would there be salts below? Well, on a chemical basis, One thing all salts love to do is dissolve in water. You can do this in an experiment at home. You take an ordinary glass of water, you take some salt, you shake it in there, stir it up, and hey, it dissolves. There we go. That's how it works. All salts love to, not sodium chloride does, and so does magnesium sulfate hexahydrate. They don't sell that at Walmart. But all these salts, they love to dissolve in water. So, okay, everybody wants to find water. So here's the cool bit. What if the thing smashes into Ceres, knocks a bunch of material out, a bunch of ice and watery sort of material comes up from under there, comes up to the surface, but then the sun bakes it. All the water goes away. All the water, evaporates off, sublimates off into space. And what's left behind? Well, the salt is. The salt's not going to evaporate. So that's kind of the working hypothesis. There have been a couple of papers published calculating, okay, how much would it take to get this and all that, and that seems to work pretty decently. So that's an idea. Or maybe we're totally wrong here. Again, this is something that was not known until about a year ago. And so we're at the fun stage of the scientific process. We have data, we have interesting data, we have amazing data, we have strange, bizarre data. And now it's just try to put those pieces of the jigsaw puzzle together. And Dawn continues to send back the pictures. It's sending back the pictures every day. It's orbiting so low now that it's giving really, really detailed and specific pictures so we can see in more detail what's going on. Cool. Well, there's a report. There's the Dawn mission. NASA's Dawn spacecraft, it orbited around the asteroid Vesta for 1 year, then left and traveled to Ceres, and it's been orbiting there for more than a year. It's these crazy, amazing new ion engines that have allowed that to take place. With ordinary chemical engines, we could have done one or the other, but not a chance could we have done both. And it would have been very hard to do with only 1,000 pounds of fuel to visit 2 different asteroids. That's amazing. Dawn confirmed that these HED meteorites here on Earth originally did come from Vesta. And Vesta is this dense rock metal sort of object. Lots of interesting things going on there. And the bright spots on Ceres are deposits of salt on the surface, perhaps left behind by ice that was burned away by the sun, or maybe something else. And it's going to be there. It's going to be sending back data for the next year or so. All right, thank you very much for your attention. The next astronomy event we're going to have here is one of my very favorite movies of all time. Is a movie with Tom Hanks and all that, Apollo 13. On Thursday, April 7th, I'm going to give a lecture just talking about what an awesome movie it is and all the great science behind it. And then we're going to show the movie right here on the big screen. It's going to be fun. So please come and join us for that. Thank you for your attention. Does anyone have any questions about the Dawn mission? Yes?
What's the surface temperature of those asteroids?
Good question. What is the surface temperature of those asteroids? I can't give you a number off the top of my head. They're a little bit farther from the sun than Mars, so their average surface temperature would be dictated by their distance from the sun. A little bit cooler than Mars is. Mars is pretty cold. A little bit warmer than stuff on Jupiter, something like that. Yeah. Good stuff. Other questions? Yeah.
What about ion engines are?
Well, I mean, the ion engines work as you got enough fuel, and getting here and there, that pretty much took care of the fuel. So that's good. It got us there. That's what we had. That's what we had to do for. Wonderful. Yes.
So I guess on a basic level, I would expect manganese iron ratio to be the same on the moon and Earth. And it's showing the
That's right. What a wonderful. So why is that? Why would the Earth and the moon be different? Great question. Because the main theory of the formation of our moon is that when the Earth was forming, 4.5 billion years ago, it was just almost kind of formed, and then an object about the size of Mars came along and smashed into the Earth, knocked a whole bunch of material out of the Earth's mantle into orbit. Lots of stuff went all different directions, but then some of the debris of that collision then formed into the moon. So on that basis, I would expect that the moon and Mars to have very similar sort of compositions. Here, let me flip back to that graph again. It's a cool graph. I love graphs. There we go. Where are we at? There it is. So this is interesting. So you notice that these guys from the moon and these guys from the Earth are distinctly different. I mean, that's a substantial difference. So that must tell us something about the formation of the Earth and the Moon, and that there's some key difference there. There was different levels of manganese brought by this impacting object, this Mars-sized object which formed our Moon, and so more of that ended up in there. That kind of makes sense. It's still an interesting thing. There are other elements where you see very, very similar ratios between the Earth and Moon. And so the fact that there's this difference, that's interesting. I'm not sure that we have a really solid explanation for that in detail. Good question. Yes?
It's the reasoning asteroid belts developed between Jupiter and Mars as opposed to anywhere else in the solar system.
Because that was a place where Jupiter's gravity essentially kept things stirred up there. And Jupiter is huge. It is 318 times the mass of the Earth. It is a dominant object in our solar system. 2.5 times more massive than all the rest of the planets combined, even big planets like Saturn. It's a big object. So in the neighborhood of Jupiter, its gravity with these orbital resonances kept this stuff stirred up. It kicked out lots and lots of material, which would have, in the absence of Jupiter, formed another planet just beyond Mars. And so kept it from, got rid of most of it, so what was left could not form a planet. It's the proximity to Jupiter that allowed the asteroid belt to form and then remain there, and then nothing else happens. Good. All right. Yeah.
One of your earlier slides, that had the position of the Trojan asteroid.
Aha!
What did it talk
Wonderful.
about
Yeah, good question. Oh, I didn't even mention those. Cool. Where are we at? Is Jupiter known? Oh yeah, good. All right. Turns out there are some asteroids which are not closer to the sun than Jupiter, but are pretty much in Jupiter's orbit. There's a group of asteroids. Turns out, again, Jupiter's gravity is a dominant thing. It really has an enormous impact in our solar system. And so there's a complicated, messy way that the sun's gravity and Jupiter's gravity allows there to be a stable point right here. It's a Lagrange point where where things balance out. So you can put a whole bunch of asteroids there, and then they're happy there. They're going to be fine there. It's relatively stable. There's a group in front of Jupiter, and there's a group behind Jupiter, a certain 30-degree angle away from Jupiter, where this nice stable point where they're balanced with Jupiter and the sun's gravity. And so we see populations of asteroids there, not between Jupiter and Mars, but in Jupiter's orbit itself, at these certain specific angles away from Jupiter. Wonderful. All right. One more? Yeah.
So, kind of off the subject, but, so if you have water, is there carbon, and do we have what we like?
Ooh, wonderful. There you go. That's why everybody's interested in water. Is there carbon there? Sure there is. There's carbon everywhere in the solar system. Lots of these minerals have carbon, and so then that's what people talk about, especially when we begin to. It's one thing if it's frozen, okay, that's fine. But liquid water, if there's active geology on Ceres, if there are things making mountains and grooves and stretching and squashing the crust, that indicates motion underneath. And solid things don't move, liquid things move. Now, I don't know what would be warm enough to be keeping the mantle of Ceres liquid. And again, we still don't know for sure it really is water. But if there is a liquid mantle of water there, then that offers some really interesting possibilities. And that's something that Dawn isn't going to be able to answer. But future missions could. If we had like a ground-penetrating radar mission, then that could tell us a little bit more about what's going on in the mantle, at least see if that's possible. On the other hand, I don't know if living organisms would like living in a salt of aluminum, hexafluor, or whatever that sort of stuff was. That might not be so good, but that's really interesting. Wonderful. Well, thank you all for coming this evening.